right, so our next presentation, Dr. Wayne Coblentz from the USDA Forage Research Center is going to talk a little bit more about some of the factors that affect silage fermentation. Thank you, sir.
Thank you. Good morning. Am I on? Can you hear me? Good. In response to the question that was just asked too, something that was been my experience, the cases of botulism that I've dealt with, which have been very few, are frequently associated with ensiling a dead animal. And that is frequently a very common cause of botulism. A rat, snake, squirrel, something. So, and if that's the case, it'd be a very localized problem. So, anyway, for what that's worth. They asked me to talk today about factors that affect baled silage fermentation, and this would include some work that we've done in Wisconsin, and then I've drawn on work from other individuals as well. Excuse me, I'm going to have to put my glasses on. Okay, Dennis made this point, but I think it's a very important one to make. Regardless of the type of silo, most management principles are the same, and one of the most important principles is to start with high-quality forage. It doesn't matter how much you pay for this piece of equipment or a baler or whatever you're buying. If you put garbage in that silo, you're going to get garbage back out of it. That's pretty much the way it works. The overall goal of silage fermentation has a couple parts in my estimation. The first one is to establish anaerobic conditions, which is essentially no oxygen. Now, whenever you incorporate a forage mass, you're going to trap oxygen in that forage mass, and that is going to be removed through respiration of still functioning plant cells. The object is to make that occur as quickly as possible. What you do not want is to delay sealing or allow air access that's going to prolong that period of removal of oxygen. So if you seal it promptly, you're going to prevent air from re-entering and recirculating through the silo. You're going to prevent decay, prevent losses of dry matter and energy, and possibly production of toxic compounds. And we'll talk about some of those things as we go through the presentation. Another goal is to establish conditions within that silage mass that encourage the proliferation of desirable microorganisms, but discourage undesirable ones. Desirable ones would include primarily lactic acid producing bacteria. That's what you want to encourage. Undesirable ones would include clostridia, enterobacteria, yeast, molds, and all sorts of other things. Ultimately, ideally the goal is to establish a stable silage mass by lowering the pH and maintaining anaerobic conditions. So what you really want to do here, and Dennis covered this quite well, is you want to convert plant sugars into lactic acid. That's the overall goal. And in that process, there's a couple different pathways by which that occurs. One is a homofermentative pathway in which simple sugars like glucose and fructose are converted primarily to lactate. That's obviously highly desirable. There's also heterofermentative processes in which those simple sugars are not only converted to lactate, but also acetic acid and various alcohols and other things, which is obviously less desirable. But both pathways do occur. I thought before we start here, I would really take a minute and just talk a little bit about some of the characteristics of different types of fermentations. And before I do that, I want to point out this work is from Northern Europe, actually from Scotland. They have very poor wilting conditions in that part of the world, and historically they have direct cut many perennial cool season grasses. So these forages, these silages are chopped. They're perennial cool season grasses. You will notice that they have very, very low dry matter concentrations, so they're extremely wet. I want to say that as a preface. But however, I think it's instructive because they've really summarized what you can look at and get an idea of what to expect with different kinds of fermentations. The first one is a lactic acid fermentation. Some of the telltale signs of that are excellent production of lactic acid, a very, very low pH, 3.9, and very little residual water-soluble carbohydrates or sugars. Lactic acid is a very strong acid, particularly compared to some of the other potential acid products. So that's why you really want to encourage the production of lactic acid. It will drive the pH down more substantially than acetic acid or some of the other potential products. Now, what they called wilted here is more what we would call traditional silage, and it's still fairly wet. That's 69% moisture. You will notice that the pH is a little bit higher. Wilting does restrict fermentation, and we will talk about that in a minute. There is still excellent production of lactic acid, and there is a little bit more because the fermentation is restricted. There's a little bit more residual sugar in there. We've had some discussion of Clostridial fermentations. They are typically a problem in very, very wet forages, and normally it's a secondary type of fermentation where the pH will start to go down, but you can't establish stability, and then it will go back up because there's some secondary fermentation. Particularly, lactic acid is converted to butyric acid, and you'll notice that the butyric acid is very, very high. Another telltale sign of a Clostridial fermentation is a very high concentration of ammonia. Cattle typically will not want to eat this type of forage, and you'll wind up hauling it back out in the field as manure. You can have an acetic acid-dominated fermentation, which is characterized by a large concentration of acetic acid. This is undesirable in many respects because, again, that's a weaker acid, so the pH is somewhat higher. And also in Europe, historically, they have used formic acid and some other things, which we don't typically do here, to sterilize the silage. So most of these parameters here, with the exception of pH, because you've applied acid, reflect the condition of the forage at the time it went into the silo. So that should give you some perspective on what to look for as we talk about these things throughout the presentation. There are a lot of plant factors which affect the fermentation characteristics of forages. The two primary ones that I want to talk about are water-soluble carbohydrates and buffering capacity. And when you talk about water-soluble carbohydrates, or simple sugars primarily, there's all sorts of variation in the amount that can occur in any forage plant you might want to ensile. Some of the things that will affect it include species, cultivar within species, stage of growth, time of day, climate, drought, frost events, nitrogen fertilization rate, rain, poor extended wilting conditions, various other management issues, and probably all those interact with each other. So it's a complicated mess to actually know exactly what kind of sugar you're going to have. What you really like to have, though, this picture was taken during my PhD work at Kansas State University, and on that particular day, it was 100 degrees out and the wind was blowing 30 miles an hour, which is pretty typical weather for Kansas in the summertime. And in that particular case, there was very little problem getting that material from 80% moisture, which is what a standing forage plant usually is, down to 60 or 55. It occurred very quickly. You would like to have conditions where you can get that down immediately because it does start to suspend respiration within the plant, and it stops chewing up sugars at such a rapid rate. Other things will affect the amount of water-soluble carbohydrates as well. The winter hardening process, for instance. We've been working a lot with fall-grown oats in Wisconsin, and we've noticed that when these fall-grown oats get zapped by really cold weather a couple of times, they'll accumulate enormous amounts of sugar. I mean, we've found water-soluble carbohydrate levels in some of these forages in excess of 20% of the total dry matter. So there's a lot of things that will affect the amount of sugar that's in a plant. I took this table from the University of Florida Extension website. I thought they did a real nice job at characterizing these things, so I saw no reason to change it. But what they did is just look at a number of forage plants and different types of forage plants that mostly would apply in Florida. But you'll see that corn silage, which is called the perfect silage crop, has a very high concentration of sugar. So do forage sorghum, sorghum Sudan. Cool season grasses typically are pretty high as well. And then you get into legumes like alfalfa, which are somewhat lower and make them more problematic in terms of getting a good fermentation. Perennial warm season grasses like Bermuda grass, Bahia grass typically will have very low concentrations of sugar. So if you want a really good fermentation, that can be a real problem. Another thing that will affect water-soluble carbohydrates, and again, there's a great many things, I can't begin to touch on them all, is simply nitrogen fertilization rate. This is some fall-grown oat that we've worked with recently in Wisconsin, and we applied various N rates in the form of urea, and you can see that in both years, 2011, 2012, these forages were harvested at boot stage. Very strong linear trend for a decline in water-soluble carbohydrates just as a function of nitrogen fertilization. Of course, these levels are very, very high and probably in excess of what you would need for a good fermentation, but still the effect is very clear. Another thing that will impact the amount of sugar in a plant is rain damage, and I'm sure that doesn't really surprise anybody in here. This is some work that Rich Muck and I did a couple of years ago with rain-damaged alfalfa. The bars that you see on your left are the initial concentration in the green of sugar, about 6% of the total dry matter, and the yellow is the concentration of starch. On the right, after a little more than an inch of rain, this has been depressed to about 4% of dry matter for water-soluble carbohydrates and less than 1% for starch. Now, the reason I put the starch up there, the circumstantial evidence here would indicate it to us that some of this starch is being mobilized after a rainfall event, and you may actually get some buoying of the water-soluble carbohydrate levels. They may not depress as rapidly as you may think, depending on the circumstances. This is a similar kind of arrangement, except we had nearly 2 inches of rain, and actually the exposure period was like a week or more. And again, we started out with about 6% water-soluble carbohydrates, 2% starch, and after that prolonged exposure period, we're down to a very low concentration of sugar and very, very little starch. So again, this is going to affect the ability of these forages to ferment properly. The other thing that I want to touch on briefly is the buffering capacity. All these forages are not created equal. What a buffering capacity really is the inherent resistance to pH change. So you'd really like that buffering capacity to be very, very low. Again, corn has probably about the lowest buffering capacity. It's the perfect forage to ensile for that reason, as well as the high sugar content. Some of the cool season grasses are somewhat higher. Problem is when you get down to the bottom of the list, you have a lot of legumes. Alfalfa is very highly buffered, which means you have to make a lot of acid to get that pH to go down, and that can be a problem. The other thing that's also a problem is that the buffering capacity tends to be much higher with more leaf. So if you have rain damage, for instance, while that's a negative, that actually may reduce the buffering capacity because you're going to wind up with more stem in whatever it is you bale up. As the plant gets more mature, the buffering capacity actually goes down. Dennis touched on this, but this is really, really critical, I think, for baled silage, and that's to manage moisture content. Generally, baled silage should be packaged between 45 and 55% moisture, according to Kevin Shinners in Wisconsin. You'll see some other recommendations that may vary a bit for that. But the key point is the average for the whole field or the whole group of bales should be somewhere around 50 or 55. That doesn't mean you wait till it's that point to start. That should be the average of whatever it is you bale and wrap. The production of silage fermentation acids, however, is positively associated with moisture concentration. The wetter the material is, the more fermentation acids you're going to produce. So this creates a little bit of a difference with traditional chopped silage because the typical recommendation for anything you'd run through a forage harvester is to make sure it's less than 70%. So there can be a difference there of about 20 percentage units in dry matter and still be within recommendations between the two silage types. As a result of those factors, baled silage fermentation tends to be inherently restricted and results in a greater or less acidic final pH, and we'll show you some examples of that. This is very dated work dating back to the early 90s, Nicholson's work with alfalfa, and he baled alfalfa at 2 moisture concentrations, 60 to 65%, which he called high, and 49 to 54%, which he called ideal. And what we have is the fermentation profile here at various points during that fermentation process. But in the interest of time, I'd prefer you just looked at the end point out here at about 2 months. You'll see that there's significantly more production within this baled alfalfa, significantly more production of lactic acid at 58 days, also more acetic acid and more production of total acids. As a result, when you look at the pH of that ensiled material, what you're going to notice is that the ideal moisture, the pH went down more slowly, and you wound up with a final pH of about 5.2 or 3. It's a more rapid decline with the real high moisture, with a final pH of about 4.7 or 8. And that's a pretty typical response to moisture in these kinds of forages. This is some work, again, that Rich Muck and I did with large rectangular bales of alfalfa, where we have bale moisture on the x-axis and the lactic acid concentration on the y-axis. What we found in this particular case is until you get up to about 45% moisture in these alfalfa bales, you actually may not be able to detect any lactic acid at all. Now, that's not to say that there's not acid produced. That's not to say that you won't see a pH decline. But in these drier forages, you may not see a whole lot of lactic acid produced. You may not be able to detect it. All right, what about the opposite extreme, the opposite problem? And we've talked a little bit about that here already this morning. What we're really concerned about in wet forages is the potential for a clostridial fermentation. The end products principally are butyric acid and ammonia. Again, this is typically viewed as a secondary fermentation in most cases, where you start the normal fermentation process, but the pH is not suppressed sufficiently. And what happens is the lactic acid and simple sugars are then converted into butyric acid, which is highly undesirable. There's also extensive ammonia protein breakdown, and it winds up in the form of ammonia, and you wind up with a very nasty product. There are some characteristics of high-risk forages. Anything with high moisture concentration. If you remember back to the slide I put on from Northern Europe, a lot of the research in Northern Europe has been specifically oriented to address this issue of clostridial fermentations in very, very wet silages, because that's the way they do business over there, and it's a big problem. Direct cut forages can be at high risk, with the exception of corn. Immature, rapidly growing forages, anything highly contaminated with dirt, manure, or both. Anything with low sugar content, very high buffering capacity, forages with very high protein concentrations, legumes generally are a problem, and also any non-homogeneous forage, such as in a baled silage, where you may have pockets in there of really wet material interspersed throughout the bale. They can be subject to a problem. So the best prevention is to wilt the material prior to ensiling, which we can for the most part do in this country. And as such, because the recommendations for baleage are for a lower moisture content, there's generally a fairly low risk, but that's not to say there's no risk. Again, just to emphasize this, these clostridia are associated with the plant in the field. When you incorporate them into the silage mass, they're looking to attack sugar, lactic acid, and proteins, and the end products are butyric acid, ammonia, and you wind up with a highly undesirable product. One of the recent pieces of work that we've done in Wisconsin, and this is more of a problem in a dairy environment like that, where there are times during the year where people have manure pits that become full for whatever reason. And they become desperate to create room in that reservoir because they're at risk of running them over. And we will periodically get questions about how much risk is associated with applying dairy slurry to growing alfalfa. And so we did a project with that. Rich Muck participated in this as well. We had slurry application, 4 treatments, no slurry. We applied it to stubble, 1 week of regrowth or 2 weeks of regrowth. And we used my environmental microbiologist I work with, Mark Borkhardt, developed some qPCR methods to quantify the clostridia in these forages. Generally what you'll notice is the counts, and these are log counts, so these are actually very high numbers. The log counts are always lower without slurry applied, but they do exist. So there is clostridia associated with these forages at the time they're ensiled, even when there's no manure applied. But they tend to go up whenever you apply manure. Generally, if that application is delayed onto a growing plant, the counts are also higher, and after ensiling, they tend to be higher. Most of those things you would probably intuitively expect. Now, having said all that, that doesn't mean that if you apply slurry, you're going to wind up with a clostridial fermentation. In fact, with this alfalfa, which we put up at Balage, we could not distinguish between the fermentation characteristics of alfalfa that had slurry applied against those that had no slurry applied. We could not detect any difference statistically in the general quality characteristics of the forages. So that doesn't mean that you're going to get a clostridial fermentation, but it does mean that you have greater risk and should be aware of it. And there are some management things you could consider in that situation. So if you compare baled silage with precision chopped haylage, how do they compare? Well, we've already talked about moisture effects. You're going to have a restricted fermentation because baled silage is going to be drier. There's also another thing that potentially causes a difference. In baled silage, the sugars within inside that plant have to diffuse to the outside of the plant where the lactic acid bacteria are adhered, because you don't have any chopping action that facilitates mixing. Also, it's dependent on the operator and a lot of other factors, but the dry matter density in baled silage can also be lower, which also may restrict the availability of sugars to the lactic acid bacteria. What this suggests is that even if the moisture concentration is the same between baled and chopped silage, there's going to be an inherent restriction in baled silage. This is again Nicholson's work that dates back about 20 years, but it illustrates this point extremely well. He had a mean moisture content of 61% for alfalfa that was ensiled in large round bales or precision chopped. If you look out here for lactic acid out at 58 days, you'll see that the production of lactic acid was roughly 2.5 times that of the baled silage. The production of acetic acid was also greater. Production of total acids were nearly twice as great in this particular case. Oops. Sorry. What does that do to the pH? Well, if you look at the pH progression across the fermentation period, you'll notice that for the baled silage, the pH depression is much slower, and at the end it exceeded 5 pH units, as opposed to the chopped silage, which was down closer to 4.4. So this is another inherent restriction in the fermentation process that's associated with baled silage. Mike McCormick in the LSU Ag Center did some work with ryegrass baleage, annual ryegrass baleage, and chopped ryegrass some years ago. In this particular work, the moisture content there on your left is about 60% for both of the silages. And you'll notice that after they were ensiled, the final pH was depressed for the haylage as opposed to the baled silage. there was greater production of lactic acid as well. This acetic acid, again, is not really desirable. In the end, you wound up with a lower pH because of the lactic acid that was produced. The last thing I really want to touch on in the time we have here is the elimination of air and how important that actually is with balage. I love this picture. This was taken in Arkansas some years ago when I worked there, and this producer did this on his own, and he hooked up a vacuum to the underneath the stack of baled square bales that he had put plastic over. And I think when he paid attention to detail, if I understand, he did a pretty good job. I think they, at some point, either through neglect or whatever, started to cut corners, and we wound up with some problems. But I thought that was pretty ingenious for someone who had never dealt with silage before. It's important to keep in mind that at the moment that forage is packaged in some kind of a silage mass, the respiratory enzymes within those plant cells, they start to work on oxygen that's trapped in there. And the result is that sugar is converted to carbon dioxide, water, and heat. And you can't completely eliminate that, but you sure want to minimize it. There's a lot of reasons for that. Those sugars are, of course, the pool of fermentable sugars for subsequent fermentation. This does constitute dry matter loss, which can be excessive if you allow this to continue. It increases indirectly the fiber content of the silage and will also decrease the energy content of the silage because those sugars are essentially 100% digestible. There are some things that you can do to improve your density, which will squeeze some of that air out of the silage mass. Dennis talked about some of this, but you'd really like to shoot for a bulk density of about 10 pounds of dry matter per cubic foot. You can reduce ground speed with a round baler. You can increase the PTO speed. Thinner windrows will increase the revolutions per bale. You want to manage the moisture appropriately to eliminate as much as possible some of the deformation that can occur. You want to maintain a constant bale size, particularly with an inline wrapper. And operator experience with a given baler is just really critically important. This is some of Dr. Hahn's work where he looked at bale density effects in alfalfa with two different moisture concentrations, and there was a difference in each case of about 2 pounds of dry matter per cubic foot. And you'll see that there's a modest improvement in pH and production of lactic acid at both moisture levels in response to that. Dan Undersander did some work at the University of Wisconsin. He baled alfalfa at 63% moisture and then delayed wrapping. The black line represents no wrap. The red line represents an immediate wrap, and the two lines in the middle represent a delay. You can see that there's a tremendous increase in temperature when you don't get that wrap applied quickly. That chews up sugars, depresses digestibility. And the other problem that occurs is that you can have damage to protein within these forages, and in the Maillard reaction, moisture is a catalyst, so the damage may be far more severe than it would be in hay. This is similar work with a delay of whole crop barley ensiled in large round bales. It was done in Canada, and when they had a wrapping delay of 19 hours, you can see there's a fairly significant pH increase in the final pH of the silage. So quickly to summarize, forage crops differ, learn their characteristics. Most principles of management for conventional chopped silage still apply to baled silage. Moisture management is absolutely critical. Generally, baled silage techniques will accommodate drier forages better than relatively wet ones. Fermentation may occur at a slower rate for baled silage because forages are ensiled on a whole plant basis, and the forage is usually drier than chopped silages. As a result, producers should diligently address other management details, such as maximizing bale density, applying plastic wrap promptly and properly, protecting the wrap product until feeding, and really be diligent about elimination of air from these types of wrapped forages. And with that, I'll quit.
Time for a couple questions.
Yes, sir.
On these highly buffered forages like the legumes and small grains, how important is it to use an inoculant when you're baling?
We've had a couple discussions about that yesterday. He asked about the use of inoculants on certain kinds of forages that may be at risk. My experience in Wisconsin, and I'm not suggesting that I have a great cross-section, but I don't notice people applying inoculants typically to alfalfa when they wrap it. I think they do a pretty good job of getting the wrap on quickly and maintaining anaerobic conditions. But I don't see that happening a lot. The fermentations typically are restricted anyway, so it begins to become questionable how much improvement you're really going to get from that. You're really maintaining that forage on the basis of maintaining anaerobic conditions much more so than a depressed pH like would occur in a typical traditional silo.
If I could add to that, my perspective in the southeast is I like to recommend inoculation, not necessarily for the fermentation support, but for stability support. Because in our environment it's very hot, oftentimes even in the winter months when we're feeding, and there's a very real risk of spoilage and some damage that can occur there. So I like to recommend one of those heterofermentative inoculants, or at least or maybe even a combo product that will produce a little bit more stability in the feed out phase for us.
There's at least one inoculant that has an oxygen scavenger to help get the oxygen out.
Yeah.
Yep. I won't bail without it.
One more quick question.
Yes.
Sorry.
Go ahead. I'll ask later. I was wondering about a lot of the silage balers that you can buy now. You can buy the optional processor on the front that cuts the hay up into smaller lengths. Is there any work showing that that's beneficial?
I think Dennis did that work.
I'm sorry.
He's talking about the cutting action, the pre-cutting action in the baler.
Conjun actually did some of that at UK, I think, didn't you? With that, did you have a chopped baler, chopped condition that you were
Yeah, I had
okay.
not many, not much.
Yeah, yeah. In our experience with that, I'd actually recommend to those who are actually buying a new baler to always get that as an option, because it does make a difference with regard to fermentation and some of the characteristics he was talking about in terms of better fermentation, and as well as just a management of feed out and that sort of thing, especially if they're doing any kind of mixing of ration.
In Wisconsin, that would be the primary reason she would use that too, is to facilitate putting it into a mixer wagon and preparing a blended diet.
All right, let's give Dr. Coblentz a hand.